stage 2. Our first presenter is Dr. Andrew Zonenberg. He is with ioActive. He's a senior security consultant, and he will be presenting the Antikernel, hardware and unprivileged software. Please welcome Andrew.
Hello, everyone. Ooh. We good? Okay, so I am going to be presenting on the Antikernel, which is a decentralized hardware and software operating system. This was joint work with Dr. Yenner at RPI, who was my PhD advisor a couple of years ago. This work grew out of my dissertation. So fundamentally, why are we here? SCADA OSs have problems. Everybody knows this. This is why we're here. The OS's job is to protect the system. We don't want the OS to be a liability. We don't want it to be a point of attack. We don't want it to provide the attacker with opportunities to go and make whatever they're doing even worse. So starting with the unpleasant fact that kernel mode means you have access to everything. And what level of code, what piece of code in a modern OS actually needs access to everything? You've got the internal state of the memory manager. You've got the buffers of memory mapped I/O. You have the private heap data of user-space process. No one part of the system needs access to everything. So why do we have any software whatsoever that has access to all of this? It just seems like a bad idea. Fundamentally, what this tells me is that any system that has any code whatsoever running in ring 0 is violating the principle of least required privilege. So here's the question. We can conclude based on this that it should be possible to build a OS in which we don't have any code running in ring 0. But this just tells us it seems like it should be possible. It doesn't tell us anything about how we actually build it. So we're going to look at some existing kernel architectures. The first is the monolithic kernel everybody's familiar with. You've got one big block of code running with full privileges. It does everything. Any code anywhere in there can corrupt any state anywhere. Then we move down to the microkernel, where you move drivers and a lot of stuff that doesn't really have to be done in privileged mode out to a user-space server, and you have the kernel handle a smaller amount of stuff. Then the separation kernel is kind of taking this to the logical conclusion, in which the job of the kernel is simply to take the various security domains in your system. You've got different applications that don't trust each other. The separation kernel's job is just to separate these from each other, allow them to talk to each other and control access, so certain applications are not allowed to talk to certain other ones. And now we're going to get onto a few lesser-known architectures, in particular the Extra Kernel. This was developed by a group at the MIT Laboratory for Computer Science in the mid-90s, and they weren't even thinking about security. The focus of the Extra Kernel was performance. And what they saw is that OS abstractions often are bad for performance. If you're just trying to store some temporary data on disk that's too big to fit in RAM, why do you need a directory tree and a named file system? It's just getting in the way. And so the extra kernel philosophy is to split the protection and segmentation of resources from the abstraction. The driver's job is simply to take a resource, divide it up into chunks, and control access to those chunks. And from there, everything else is done in either an unprivileged user space service or a user space library that you link with your application, etc. And so this gives an example of what an extra kernel could look like. We have a database application that is able to talk directly to the disk cache and then to the disk driver. We could have a DHCP server that just serializes leases to disk so that if you restart the server, it knows who had what IP address. There's no reason for it to have named files to do this. It just needs some block of disk it can store stuff in. So you just write stuff straight to the block device driver, and then your word processor might actually want to go through a file system so you could have named documents. And each of these individual resources are protected from each other. If the word processor tries to open the raw disk block that's owned by the DHCP server, it's not allowed to, and so on. And so now we can plot the extra kernel on our graph all the way down here. It's small and fast. So one of the key insights that the original MIT paper missed is that it's not just a performance benefit if you switch to an extra kernel architecture. If you're moving these non-security related abstractions out of ring 0, now you're shrinking the trusted computing base and shrinking the attack surface. And the original paper didn't even touch on this. I don't think they understood the true implications of their architecture. It is great work, they just didn't realize how good it was. And so let's think about what the kernel actually has to do. You obviously need some way of sharing CPU time between multiple processes. If you have one CPU per security domain, as some papers have proposed, yeah, it's pretty easy to isolate them, but your system also scales ridiculously poorly. Now, once we have these multiple applications running in the CPU, we need some way of allowing them to talk to each other. We need some way of allowing them to talk to hardware. And we need some way of managing memory at the page level. Everything below pages can be done by unprivileged applications in your libc heap or something like that. The OS's job is just to separate the pages from each other. So now let's think about if we really need each of these things to be run in ring 0, or if it's just an OS service that can be provided at some other level. So barrel processors and hyperthreading already exist. How much of a stretch is it if we have a CPU that's already able to context switch without software intervention? How much more work is it to have that CPU also schedule these threads? It's not that much. So what if we move the whole run queue into the CPU? Now, if we're doing a simple round-robin thread scheduler, which is perfectly fine for a lot of embedded systems, it gives you deterministic performance, it gives you simplicity, it's easy to verify that it does what it's supposed to, and the amount of logic you actually have to add to the CPU to do this is next to nothing. You need one FIFO, where if you have, say, 32 threads, you need a 5-bit wide 32-entry FIFO. That's nothing compared to the size of a modern CPU. And all you have to do then is provide an API to this FIFO that allows applications to create new processes, to terminate themselves, etc. And the other nice thing about this is that if you have it as this isolated subsystem, there's no possibility of you messing with any state that's outside of this. You have a physical piece of memory somewhere, you have a read and a write pointer, and you have a block that allows you to introduce a new entry in this list. You have an option to delete an entry if you're terminating a process. And so it's a little hard to read on this screen, but this is the Verilog module signature of the thread schedule on our prototype. And you can see we just have at each pipeline stage, we have the thread ID, we have a Boolean thread active value, and then we have a control bus that has opcode, thread ID in, and an OK and done result. So this is the sum total of our API. And since this is running in hardware, these are physical wires. It is very easy to just go look at the net list of the system and see these are the only wires between block A and block B. Therefore, this is the sum total of our data flow. And so this provides properties you would expect from an extra kernel and a separation kernel. We have very minimal abstraction. One of these process IDs corresponds to some unit of CPU time. We have an API for it in which we can create and destroy processes, and it is an isolated subsystem that has a well-defined interface. So now let's think. We've got these applications. We can share CPU time between them. Now, how do we have them talk to hardware? So what if instead of using a shared bus, we use a packet switch network? In the prototype I have right now, it's 16-bit addresses that identify nodes in the system. There's no reason you couldn't do larger or smaller if your application needs called for it. And so what if we, instead of allocating one address to the CPU, what if we had a whole subnet for the CPU? So in our diagram up here, the CPU is subnet hex 8040/10. Now we have 8040 is the management address. Now we could say 8060, 8061 are different applications. And then we have our RAM and flash controller up there. So what this means is that external entities elsewhere in the network are able to distinguish where messages are coming from based on the source address of that packet. So as a little bit of aside, the design is not actually one network. I'm using two networks just to separate control and data. The RPC network is used for remote procedure calls, as the name implies, as well as interrupts and small control-related messages like that. This is 128-bit datagrams. It's typically register mapped in a CPU. And then the DMA network is used for, you guessed it, DMA and bulk data transfer. And the main properties of these networks both provide their reliable datagrams. You have in-order delivery of messages between any set of endpoints. If I send two consecutive messages to two different entities, there's no guarantee what order they'll arrive in. There could be congestion further on down the network. If I send two messages in a row to the same place, they're guaranteed to arrive in order. And the network also provides a guaranteed minimum quality of service. The current prototype network is a quad tree. I'm probably going to be switching to a 2D mesh for performance reasons down the road, but the quad tree was easier to do in a prototype. And at each hop in the routing, I guarantee of the 5 available interfaces, each one will get a chance to send every 5 packet times. So worst case, at each hop, you get 1/5 of the available bandwidth. And if you want more, you can burst. There's a fixed priority table built in right now. The lowest numbered port always gets priority unless the round robin selector wants to send, and beyond there it breaks ties by lowest port number. And so this allows us to do network-based access control. We have a CPU instruction to send and receive messages. In this system, since you no longer are trying to run a syscall dispatcher and so on in ring 0, you don't need the syscall instruction to trap to a syscall handler. So we can repurpose the system call instruction in order to send and receive messages. Then, at the hardware level, we can access the network via a formally verified transceiver module. So think of it like plugging an SFP into a switch. You've got your module, you write it to use this transceiver, you drop the transceiver in, and since we've verified correctness of the transceiver, it doesn't matter what this block of code that's talking to that transceiver is. We can guarantee the packets coming out of it are well-formed, and they're not going to lie about where they're coming from, because the transceiver has a source address. And then since the network itself is all on-chip and unavailable for any software to tamper with, there is no software making routing decisions anywhere. It's just a hardwired routing table. Basically, take 2 bits of the address, and that defines which of the 4 ports you're going out of. So there's not any opportunity for software to interfere with routing decisions. And this means we can fairly easily do a machine-checked correctness proof showing messages go where they're supposed to and nowhere else. And you cannot observe or tamper with messages on the wire. This means we can use packet headers for access control. A node in the system is able to determine where an incoming request is coming from, and based on those headers, they're able to decide whether to allow or deny that request. So at this point, of course, inter-process communication is pretty trivial. Each application already has a unique address in the network. You have the ability to send messages to any one of these addresses. So if you want to send a message to another application versus a hardware device, it doesn't matter. It's exactly the same. And this actually means you can move a resource between a software application and a hardware service without even having to recompile the client code, as long as the API stays the same. So in our example here, we have application 1 sending a message out to application 2. It just goes out onto the network and then back into the same CPU. So this provides the same properties you would expect from an extra kernel or a separation kernel. We have, obviously, there's a requirement for components of the OS to be able to talk to each other. There's minimal abstraction. It's just black box datagrams, and what goes on in those packets is up to the applications. And we also have, as in a separation kernel, we have strong authentication of the origins of a message, and we can grant or deny access to a specific resource based on the origin of the message. This allows us to function like a separation kernel and provide strong protection so that one application or service is not able to talk to another. And so, of course, the obvious question a lot of you are wondering about is, what about things like malloc or sbreak or whatever the equivalent is in your system? How can you possibly not run that in ring 0? So the way we can avoid this is if we push the protection of resources out to the endpoint, which again is what the extra kernel architecture already calls for. When you create a handle and give that handle to someone, you, as the creator of that handle, are responsible for deciding who's allowed to access that handle in the future. And so we can do this all the way down to the memory controller layer. If we have the memory controller aware of which pages are free and which pages are allocated, and at the page level, mind you, there's not really that much that has to be done. This means we don't have to worry about protection in the processor MMU anymore. You can mmap anything you want, and if you try to mmap a page that you don't have permissions to, nothing happens. You've just got a new entry in your page table. You're not using it. As soon as you dereference that pointer, you segfault if the peripheral says, I'm sorry, Dave, I can't do that. And the way it does this is it just sends a message back on the RPC network. It sends essentially an interrupt that says the DMA read you requested was not approved. Pretty much the equivalent of an ICMP host prohibited message. And so this means that in order to allocate a page, all we have to do is we send a message from, say, in our case, the application is executable echo FW, which is echo firmware, sends a message to RAM, allocate. RAM responds about 30 clocks later, saying, OK, this is successful. We successfully allocated a page of memory, and the address is physical address 0 within RAM, because this is the first page we've ever allocated. Then the next thing we do is the application sends a message to the CPU. If we back up a slide, you can see that the CPU has an out-of-band management address. So in order to create a new entry in the page table, you're not poking random data structures somewhere in memory that are entirely processor dependent. you send a message to the CPU using the CPU's defined API for creating a new page table entry. And that page table entry simply says, I'm requesting a new entry at physical address 0, virtual address 40, F800. And the CPU then says, all right, fine, you've got a valid page entry there. We're going to go create a new TLB entry. And then after that's done, we allocate another page of memory. I believe this is stack and this is BSS. Then we do a DMA write, which doesn't show in this capture because I'm only looking at control plane traffic. And we get a message back from RAM saying, hey, successful write to this page. So the data structures required for doing this are trivially simple. You have a FIFO of 3 pages. You have an array storing an owner for each page. The control state machine for this is microscopic. It's a couple hundred lines. And that's in a hardware description language, which tends to be a lot more verbose than something like C. If you were writing this in C, it'd probably be 20 lines of code. And it is also fairly easy to test and verify this as a result because the logic is so simple. So we currently have a fairly thorough automated test suite. It is not formally verified yet. That is on the agenda for the fairly near future. We're a little bit short on time, so I'm going to skip over showing the extensive details of what the allocator does. But this is the sum total of what it takes to implement malloc in this architecture. And free is pretty simple as well. There's a tiny bit more than is shown on these slides. This is the logic to take a page that we've successfully confirmed, okay, you do own this page, you're allowed to free it, push it back onto the free list. It also zeroizes the content of the page to prevent state leakage. That logic isn't shown on this screen, but there's, again, not a lot of code involved. And so this provides the properties we would expect from an extra kernel or a separation kernel as well. The memory is managed at a very low level. We don't have any complicated heaps or arbitrarily sized blocks. Any of that is done in your application. The OS only takes these pages, protects applications from messing with each other's state, and doesn't even do anything like virtual memory or paging. If you want anything fancy like that, you have to do it yourself. Address translation, for that matter, is not provided by the RAM controller. It's provided by the CPU. You could have a CPU that uses raw physical addresses if you wanted to, and sure, you have to deal with the fact that you're going to go get a page and it might come back at any physical address you want. So translation is probably going to be convenient if you want to be able to ever allocate a virtual buffer more than 1 page in size, but the architecture does not inherently require it. And it is specifically not required for security. Writing to the page table is an unprivileged operation. And of course, we have the separation kernel property that no data flow is allowed between pages with different owners. So at this point, what's left in ring 0? There isn't anything left. Now all the privileged instructions in the ISA are unnecessary. Delete all of them, run user space in bare metal, and you're now left with what I've termed an antikernel because there isn't a kernel anymore. There is no software whatsoever running in ring 0. The CPU does not even have the concept of privilege rings. Everything is unprivileged. So now we can plot an antikernel on our graph here. It is microscopic, even smaller than an extra kernel because we don't have any software in ring 0 whatsoever. On the speed side, on the speed axis, I did draw a fairly large box. This is intentional because since the architecture is currently in prototype phase, we haven't really put any effort into optimizing it, so we don't really know how fast it can get. The current prototype isn't all that fast, but that's because the CPU that I built was designed by a grad student in a couple of months, and I wanted to graduate. So the L1 cache has a missed latency of around 50 or 60 clock cycles. Nothing in the architecture requires this. It is more important that the system be functional and that I be able to show, yes, it works, than it be fast. So it is unknown at this point just how fast it can be. The conjecture is that since it pretty much is an extra kernel with hardware acceleration, it can be at least as fast as an extra kernel, maybe even faster. But that remains a question for future research this time. And so this is not just a hardware microkernel. A hardware microkernel would imply that you have some component in hardware that still has the ability to modify all system state. But in an antikernel, instead, you have a series of independent state machines that collectively provide the properties you would expect from a modern operating system. But these subsystems are isolated from each other, and they communicate in a limited and well-defined fashion like a separation kernel. You can almost think of it as an object-oriented operating system. Each of these nodes in the network is separated from the rest and encapsulated and simply provides an API for the remainder of the system to talk to it. And this means that Since each node manages its own security state, your TCP is what you make it. If you have a crypto module, for example, that chooses not to ever allocate any memory in the off-chip RAM controller and only uses internal memory resources, then a bug in the external memory controller has zero impact on the security of your module. Your TCP is what you make it. If you choose not to depend on a given resource, then it doesn't matter. And of course, we also have the we also have the extra kernel property that by bypassing these unwanted abstractions, you can get better performance. So I'm going to briefly mention a couple of the other components of the architecture. For example, the name server's job is just to map these addresses, the 16-bit node IDs, back to a character in the prototype. There's no reason they couldn't be longer. Host names. This allows you to abstract away system architecture details. So you could have the RAM controller at one address in one sock and a different address in another one. And actually, in my current prototype, I have a unit test for the RAM controller that uses two completely different addressing schemes. One of them is backed by on-chip RAM. The other is backed by external DDR2. The same binary runs on both systems. And there's not even any additional abstraction. This is the hardware API is the same. And then, obviously, applications are able to register themselves with the name server to say, hey, I'm web server, I'm database server, whatever. We are a little short on time, so I'm not going to go into too much detail on the architecture of the CPU, but it's a fairly standard 8-stage pipeline superscalar CPU. The one thing that is unique about it is there's a hardware ELF loader. If you look at what it takes to run a statically linked ELF, there's not that much parsing of the headers required. Basically, you just find the program header table, loop over the program headers, and create a page table entry for each one of these blocks. So it wasn't that much work to do a signature check on the contents of these program headers before loading them. So now we can have the CPU itself enforcing code signing. Good luck patching that out. And this is an example of how we would create processes. If anybody wants more details on this, you can talk to me afterwards. The prototype, as of now, is just shy of 200,000 lines. That includes test cases and build tools and all kinds of infrastructure, and lots of yaks were shaven during the development. The actual critical components are quite small. We're looking at under 10,000 lines for the CPU. The name server is about 1,000. The other networks combined are a couple thousand lines. The code is all open source. It's released under a 3-clause BSD license specifically to encourage commercial use, reproduction of results, etc. And the network, as of now, as well as the name server in a subset of its functionality, has complete formal correctness proofs. So what goes in the transceiver comes out the other end, packets are routed to where they're supposed to, and so on. And so the code is available on our GitHub. The system is currently being refactored quite a bit. We're in the process of trying to reduce FPGA gate usage, improve performance, and so on. So a lot of the code is in the legacy directory, but it is there if anybody wants to see it. As far as future work, it's basically just optimizing performance. I'd like to move to RISC-V instead of MIPS, just for that seems to be the way that the architectures are going. No patents to worry about, etc. I'd like to do more formal verification. Obviously, we're looking to get a developer SDK documentation and so on, more peripherals, and pretty much bring it from a research prototype to something that's actually practical to use. So at this point, we've got 30 seconds left, so perfect time to take questions.
Hi, this is Rich Corrigan with SDG&E. What tools would you use for developing an application for this?
So the CPU as of now is MIPS. Like I said, the next generation one is probably going to be RISC-V. In both cases, you should just be using GCC to compile applications running on it. If you're creating new hardware peripherals, that will be done in Verilog using the compilers for whatever FPGA you're targeting. Down the road, I would like to go ASIC eventually. Obviously, that's quite a bit further down the pipeline. So for the time being, everything is FPGA, and therefore you're looking at the normal FPGA development tools plus just a C compiler for your architecture. There's been some discussion of moving the userland to Rust in the longer term so that you can have memory safety. That's an open question at this point. It seems promising, but we haven't really put any time into it yet.
Other questions? I don't have a real technical question for you, but I'm curious, who is showing interest in this and who do you think should show interest in this?
So this architecture is really meant for critical systems where you're willing to take a little more time to do it right. It's not meant to replace Android or iOS or something like that. Now, possibly the other iOS is the type of application that could benefit from this. SCADA gear in general, life safety systems, medical, avionics, anything like that is really what we're targeting here, where reliability and stability and that level of isolation and fault tolerance is actually important.
Okay, we have one more question.
Hi, Chris Black with the Underwriters Labs. So I hear that you're talking more embedded systems, but one of the major problems with cloud, especially containers, is the OSs are so vulnerable because of the shared resources. Is there any plan for using this in a container space?
It's not really something that's occurred to us so far, simply because we haven't really looked into what it would take to implement the full, say, Linux kernel virtualization API on top of it. It certainly is a potential use case, and I'd be interested in hearing more about somebody who is interested in doing that. Our primary target has been embedded systems simply because the current version does require fairly custom hardware. One of our open research questions is how much we can extend this into existing hardware. For example, Xilinx's Zinc system on chip is an FPGA glued to a Cortex A9 or I think an A15 in the next generation. So we'd like to explore what it takes and can we bolt this onto an existing CPU and still get some of this level of security, and that remains an open question at this point.
Okay. Oh, one more question.
What sort of tools do you use to do formal verification of the software?
So as of now, we're writing the assertions in Verilog, compiling with ioSys, and then using a SMT solver in order to, the older proofs are SAT-based, the newer ones are SMT because it scales better performance-wise since we don't have to prove 1 + 2 = 2 + 1 every time. So the older ones we're using, I believe, Minisat as the solver. The new ones are using, I believe, Z3, but the framework is flexible, so you could swap another solver in if you wanted to. ioSys is being used on top of there for both front-end Verilog synthesis and to run the temporal induction.